Alright everyone, so this is the 29th lecture in my series on algebraic number theory, and today we're going to do kind of the legwork to prove the unique factorization of ideals in Dedekind domains. So in this lecture we'll prove the following lemmas necessary to prove the following theorem. Let A be a Dedekind domain. And let's say a non-zero ideal. Okay. Then A factors uniquely as a product of prime ideals. And these factorizations typically look like a p1 to the e1 times pr to the er with EIs equal to 0. Okay, I guess, well, if I include the word proper, then I can just assume these EIs are greater than 0, and then I don't have to worry about what this uniqueness means. Okay. And here, recall, what do I mean when I take the product of ideals given A and B ideals in A, there's a product ideal A times B, which is the sum. So it's not just the product of all elements, you have to take finite sums as well. Wait, okay, let's kind of scoot this up. Okay. So in this lecture, we're going to prove, like I said, so we're not going to prove this result in this lecture. Then I'll have to wait till the next lecture. But in this lecture, we'll prove the lemmas necessary that we're going to need. Okay. And there are mainly three main lemmas we're going to prove in this. In an Ethereal ring, every non-zero ideal contains a product of non-zero prime ideals. Two powers of relatively prime ideals of relatively prime. And three, for a prime ideal P, I guess for an integral domain, and I should say a maximal ideal for an integral domain A and a maximal ideal P, we have an isomorphism A mod P is isomorphic to A localized to P mod P A sub P. So this P A sub P is going to be an ideal in the localization. Okay, so these are the three lemmas remaining that we need to prove this theorem on unique factorization, and we're just going to spend this lecture proving these lemmas. So 29.1 proposition. We're going to let A be an Arthurian ring. And we're going to let A be a non-zero ideal. And we're going to prove that A contains a product of non-zero prime ideals. Okay, so how do we do this? So it turns out all you need is this Ethereal hypothesis, and then you can prove this result. We're going to consider the set S, basically the set of ideals for which this fails. So the set A such that set of ideals in A such that A is non-zero. And what's more, and there shouldn't be a comma there. A does not contain a product of non-zero primes. Okay, and basically our contradiction, so we're going to suppose for contradiction that S is non-empty, and then we're going to show basically yeah, we're going to derive a contradiction suppose for the sake of contradiction. S is non-empty. Okay, then what? So, since A is an Arthurian, we can choose a maximal element. So a maximal element A and S, and what I mean by maximal here is I mean maximal in S, so maximal with respect to inclusion of elements of S. Okay, so this is one of the conditions of being an Arthurian ring. Any non-empty set of ideals contains a maximal element with respect to inclusion. Okay. So in particular, since A is an S, A cannot be prime. And this is kind of almost like a technicality. A cannot be prime, since we consider a single prime ideal to be a trivial product of prime ideals. So think back to like your statement of unique factorization of integers. We say that every integer can be written as a product of primes, even though some of those integers are primes, and the only way to write them as a product of primes is to just basically write that single prime. So the same thing is kind of happening here, where we consider a single prime ideal to be a product of prime ideals, a product of one prime ideal. Okay. Since A is not prime, what does that mean? Well, we can find x and y in A such that, well, neither of them are in my ideal A, but their product is. Okay. And then we're going to consider A plus x and A plus y. Well, since x and y are not in A, these ideals both properly contain A, and hence cannot be in S. Right, so since A is maximal in S, these properly contain A. They cannot be in S. What does that mean? This means that each of these respectively contain a product of prime ideals. Note also that A plus x times A plus y, if you use how we define the product of ideals, turns out that this is contained in A plus x times y, which is contained in A, since x times y is in A. There's a product of prime ideals here. Product of non-zero prime ideals, since both A plus x and A plus y contain a product of a product of non-zero prime ideals. A must as well. So notice, so if I had like P1 through PR here and Q1 through QS here, then A would contain P1 through PR times Q1 through QS. This is a contradiction because A was chosen to be an element of S. So what do we see? Well, our initial contradiction assumption was that S is not empty, thus S has to be empty and the result holds. Okay. So we've proven the first of our lemmas: every ideal contains a product of non-zero primes. Okay. This next result is not too bad either. Proposition. Let A be any ring and let's suppose I have A and B relatively prime ideals. Or, yeah. So remember, this means that they add together to give the whole ring. A plus B equals the whole ring. Okay, the proposition says that for any choice of M and N, these two ideals, A to the M and B to the N, are relatively prime. And the proof is pretty easy. By definition of relatively prime, I can find A in my ideal A and B in my ideal B, such that A plus B equals 1. So since this ideal is equal to the whole ring, particular 1 is in there, so I can find A plus B equals 1. Then 1 is going to be A plus B to the M plus N, and this thing is going to be an element of A to the M plus B to the M. Because basically either, if you think about expanding this out, each monomial in the A and B will either have M A's or N B's. Okay. And once 1 is in this ideal, then the entire ring is in the ideal. Okay, so finally we're going to prove this isomorphism of quotient rings. So we're going to let A be an integral domain. And let's say P containing A is maximal. Then I map Rv from A to A localized at P, mod P, A localized at P. It's going to send an A to A plus PA localized at P. Okay. This is going to descend to an isomorphism. And the proof is actually a little more complicated than you might expect, but it's not too bad. So it's going to descend to an isomorphism Rv tilde from A mod B. Same image. Okay. Proof. So I'm going to call this PA sub P, I'm going to call this Q, just to make things a little faster to write. So by the first isomorphism theorem, it suffices to show Rv is surjective with kernel P. Okay. So first we're going to show varphy is surjective. And then we'll worry about the kernel. We're going to let A over S plus Q. Say this is just an arbitrary element of A localized to P mod Q. And we're going to, so notice here that S here, S is, right, so elements of the localization are elements of A divided by elements of A not in P. So S is some element not in P. Since P is maximal, we must have S plus P equals A. So we can choose, right, P and P, A and A. I should call this maybe A prime since I'm already using A, such that A prime times S plus P equals 1. So here I'm already using the fact that P is maximal. Okay, so it would be a lot harder to show this. It's probably not true just in the case that P is prime. Although I'm not sure if it's true or not when P is prime. Okay, so I've got this relation. Okay. And then I'm going to consider varphy of A times A prime. So what do we have here? We have, so what do I need to show? I need to show that I'm going to look at varphy of A times A prime, and I'm going to subtract off A over S, and I'm going to show this is an element of Q. Okay, so by definition, A times A prime, this is going to be varphy. I should use, instead of varphy, I should use maybe iota here. So iota is going to be the natural inclusion of the of A into its localization. A times A prime minus A over S. This is going to be A times A prime minus 1 over S. And since A prime times S plus P equals 1, and S is a unit here, I can divide by S and get that A prime is going to be one over S minus P over S. This is A prime minus 1 over S. So this is A prime. So I'm using this equation here. Okay, simplifying things down, this is going to be A times negative P over S, which is certainly an element of Q, because P is an element of P. Okay. Thus, varphy of A times A prime equals A over S plus Q, and varphy is surjective. Okay. Now to show that the kernel is exactly P, Notice these are both, so since the image of phi is a field, because Q is maximal in the localization, the kernel is also a maximal ideal. So I really just need to show one containment. Thus, it suffices to show P is contained in the kernel. And while this follows almost by definition, from the fact that P is contained in I guess maybe if I'm being careful, I should write the natural inclusion of P is contained in Q. Okay. So we've got three important lemmas that will help us prove the unique factorization of ideals. We've got this lemma about quotient rings. We know every ideal contains a product of prime ideals, and we know that powers of relatively prime ideals are again relatively prime.